All right, so now we have done an example when we have just the weak acid, so at the beginning before we've added any base. Now let's talk about when we start adding in that base. So we have added in some base, we've added in some, let's say sodium hydroxide or OH minus, right? So once we add that in, what we get is a buffer. So we are before the equivalency point, or even before halfway the equivalency point. Um, and so we have a buffer. We can use this equation, and whenever we have a buffer, to find the pH of it. It's the pH is equal to pKa plus the log of the concentration of the base divided by the concentration of the acid. This is called the Henderson-Hasselbalch equation. You can use this, or you can just use a quack table. That's another way of doing it. The hard part is what to use for the A minus and what to use for the HA, because we have a reaction happening before um, we actually have this equilibrium that happens. So the A minus is being produced and the OH is kind of going away. So if we kind of think about it this way, so before we had just HA into the system, then a sodium hydroxide kind of comes in and makes a reaction. So we have to do a calculation for that reaction first. So what we're left over with is sodium left over, which isn't going to do anything. It's an ion of an alkali metal. Those aren't going to do anything in the solution. And then we don't count for the water. So as we add in more sodium hydroxide, you can see that our concentration of HA is decreasing and our concentration of A minus is increasing. But notice we have HA and A minus in the solution. That is why it is called a buffer. All right, so let's go over how to calculate this titration equation when we're in the buffer range. Previously, when the titration begins, we weren't in the buffer range. It was just a weak acid. But when we're in the buffer range in a weak acid strong base titration, the math gets a little complicated because it's kind of two different steps. Um, in order to use like the K expression, we need to know the concentration of the base and the acid before all the equilibrium stuff happens. So essentially what we do is we do a little bit of stoich first, and then we do the quack table. So for this example, after 8.0 milliliters of the 0.1 molar NaOH is added to this solution, which is 50.0 milliliters of a 0.1 HCN. Um, so the first thing we're going to do is we're going to write out the titration equation, the titration reaction. So that would be HCN aqueous is going to be reacting with the hydroxide ion that we're adding. I'm kind of writing the net ionic as we go. The Na is not going to do anything in the reaction, so we don't have to write that. Now this is not equilibrium, this is just a normal titration reaction. So the hydroxide is going to combine with the hydrogen to form water, which is a liquid, plus Cn minus, which is aqueous. So we can see that this would be our weak acid, and this is our conjugate base that forms when the sodium hydroxide is added. So this is how it makes the buffer. It makes the buffer by changing the acid into the conjugate base. That's how these titration equations work. Now I'm going to do a rice table. I'm going to do a rice table because it's stoich, just because I think it's the easiest way to sort of organize what's going on. So in a rice table, we have to remember that we have to do moles. Moles go into a rice table, not concentration, so we got to calculate the moles. Now, to make my life a little bit easier, I'm going to use millimoles, which is just 1,000th of a mole. So how many millimoles of HCN do we have at the beginning of the reaction? 50 times 0.1 would be 5 millimoles. Hydroxide, so we did 8 milliliters of 0.1, which would be 0.8 millimoles. Um, this we don't really care about, and we have 0 of this at the beginning. This is going to be minus x, and plus x. Now, here this is the 1-to-1 mole ratio. We have less of this, so this is going to be the limiting reactant. So this is going to be 0 at the end. So essentially all the hydroxide gets used up, which should make some sense. We're not to the equivalency point yet. All the hydroxide is getting used up. We still have acid left. That's why the pH is still pretty low. And so if this is 0, x is 0.8, which means we have 0.8 millimoles of this left. And then we have to figure out how much of the HCN is left over. So we just do 5 minus 0.8, which should be 4.2 millimoles. Now, a little trick for you. You don't need to change these to concentration. You don't have to change them back to anything. It's going to be the same no matter what, because it's a ratio between the two. If you divide both of them by 58 milliliters, you're going to get the same ratio between the two. And it's okay that it's a ratio because they end up on top and bottom of each other in your Ka expression. So I really need this number and this number. That's why we did this. Okay, so now that we did the stoic, what we're going to do next is the equilibrium. So we have an equilibrium equation. It's still an acid. So we're going to still use the acid equilibrium equation. Okay, so we're going to do a quack table. So here's where things are different. We're going to say that, so essentially the stoic happens first, and then it does equilibrium stuff. So our initial concentration here is 4.2. We don't care about that. Initial concentration of the H3O plus is 0, and the initial concentration is 0.8. This is still going to be going to the right because if this is 0 right here, it's going to push it to the right. So this is minus x, plus x, and plus x. This would be 4.2 minus x. This is x, and this is 0.8 plus x. Now we plug this into our K expression, which is up here. I'm going to kind of skip up writing out the expression. So we have 6.2 times 10 to the negative 10th is equal to x times 0.8 plus x divided by 4.2 minus x. We can say that these x's are negligible because x is much, much less than 0.8, and which is also less than 4.2. And then we solve for x. So we have 6.2 times 10 to the negative 10th times 4.2 divided by 0.8. And then that's just our answer there. So x is equal to 3.2 times 10 to the negative 9th. And then we do the negative log of that to get our pH, and our pH is 8.49. So we can see that our pH jumped from 5 to 8.49. It's becoming less acidic. Now, the reason why this number is kind of weird, the way that the pH is kind of a higher number, and that's because this is not a very strong acid. Times 10 to the negative 10th would make it a pretty weak acid overall. So it's like the buffer range is going to be higher than like 7 or something like that. So that's how we're going to do that one.